Thank you. So yesterday I was giving you this kind of overview of some of the classical theory of percolation on infinite transitive graphs. And there, I was focusing on this question of, well, first of all, when do you have a phase transition? And then once you're in the phase where you have infinite clusters, do you have one or infinitely many or 7 or whatever? Okay. And what I want to tell you about today is recent work, which is studying all the analogs of these questions for finite transitive graphs. And as I was pointing out as we were going through the infinite graph theory yesterday, actually a lot of the arguments break down, and generally speaking, the transitive graph, the finite case is actually more subtle than the infinite graph case, at least in some ways. Okay, so that's not working. That's not working either. Okay. Cool. So just to recap, one of the things I mentioned yesterday, we were talking about when you have uniqueness or non-uniqueness of the infinite cluster. And I mentioned that, the main conjecture on this is due to Benjamin and Schramm. And they conjectured that you have this phase where there are infinitely many infinite clusters, if and only if the graph is non-amenable. So actually the amenable case of this, we know by that's the Burton-Keane theorem. But the non-amenable case remains open, okay? Now, I'm not going to talk really much more about this today, but just to say, whether or not you get uniqueness or non-uniqueness of the infinite cluster depends on the geometry of the graph, right, in the infinite case. Okay, now, I want to tell you about this general theory of finite transitive graphs, but before I do that, let me just quickly recap, the most classical finite transitive graph, the theory there, which is the complete graph, right? So if you do percolation on the complete graph, that's the same thing as doing the Erdős-Renyi random graph, right? And here, of course, there are maybe tens of thousands of papers written about the Erdős-Renyi graph, I don't know. So I'm not going to tell you everything that's known about it, but the most basic thing that we know is that there is a phase transition in the existence of a giant component. So this is a component whose size is linear in the size of the graph, it's proportional to the size of the graph, okay? And what happens is if you send n to infinity, so you have your complete graph on n vertices, and you take p to go to 0 with n, then if you take p, it turns out that the interesting stuff for a giant component emerging happens when p is of order 1 over n. And if you take p to be lambda over n, and then send n to infinity, if lambda is strictly less than 1, you don't get a giant component. In fact, moreover, the components are all very small. The largest one is logarithmic in n. Whereas if you take lambda to be bigger than 1 and then take n to infinity, then you do get a giant component whose density depends on lambda, okay? So this is kind of the basic phase transition that one sees in the Erdős-Renyi graph. I guess this result probably goes back to the original paper of Erdős and Renyi. So I should mention that, as in the infinite graph case, there are many very interesting and very hard questions that come up when you try to understand the critical behavior in detail. Actually, for the Erdős-Renyi, these are understood pretty well. So, if you take p to be exactly 1 over n, then it turns out that the largest cluster has size n to the 2/3 with high probability. And, there's all kinds of interesting theory. And if you take 1 over n plus something lower order, you can get other things happening. And so, okay. So one thing to point out about this classical theory of the Erdős-Renyi graph is it usually proceeds by either some kind of direct counting argument, or maybe like coupling with a branching process very accurately, things like that, okay? So in particular, all the analysis relies on your ability to understand sort of everything that's going on very precisely and quantitatively. And in particular, you really know where the critical, where the phase transition happens, right? Which is a bit like, in the infinite graph case I talked about for the square grid, a lot of the analysis there, you have as a starting point that you know exactly that PC is a half for the square grid, okay? So that's kind of like what's going on here. You can really compute where the phase transition happens, and that's very helpful, but it's something you should not expect to be able to do in more general examples. Okay, so of course, there are a number of other, classical examples that have been studied heavily in the combinatorics literature, like hypercube, the Hamming graph, and so on, okay? And generally speaking, the stories for these graphs is similar, except you have to replace 1 over n by 1 over the degree. Okay. On the other hand, there are some examples of finite transitive graphs that have been studied a lot by probabilists, where the theory is quite different than this. So, for example, if you look at the d-dimensional torus, so you fix d and send n to infinity, as you might imagine, understanding percolation on the torus is very closely related to understanding percolation on the infinite grid. And what happens is you get this part is similar in that you have a phase transition between the largest cluster being logarithmic to the largest cluster having linear size. But now this phase transition is going to happen at PC of the infinite grid rather than 1 over n. And actually, I should say this is not an easy result. In 2 dimensions, it's fairly easy, but in higher dimensions, it's not. I mean, the proof, the sort of classical proof I know goes through something called the Grimmett-Marstrand theorem, which is a famous, quite difficult theorem about percolation on the infinite grid. Okay, and of course, if you want to understand the critical behavior, that's a very difficult question on the torus, presumably, especially. I mean, again, it's one of these things we understand quite well in 2 dimensions and in high dimensions, but understand almost nothing in between. Okay, so this project that I'm going to tell you about, we wanted to build some general theory of percolation on finite transitive graphs. In the previous literature, there are a number of these examples that are studied, but they all used methods that were quite specific to the, to the torus or to the complete graph or whatever. We wanted to have like a general theory that applies kind of uniformly to all these examples. Okay, so this kind of interpolates between these 2 settings, the setting of infinite transitive graphs where there's been a lot of work at very high levels of generality, often using ergodic theory tools, and then, this traditional finite graph like complete graph, hypercubes, and so on, which was studied with quite a distinct set of tools by a fairly distinct community. Okay. And, some questions we're going to be interested in are, first of all, when do we have this supercritical phase? Like when it could be, like if you do a cycle or something, you have to take P really close to 1 before you see giant clusters. When can we guarantee the existence of a non-trivial phase where we have giant clusters? Secondly, when we do have giant clusters, must it be unique? And does this depend on the geometry in some interesting way? Okay. We can also ask, so for these examples I just mentioned, we sort of have a well-defined notion of the critical sequence of P's in some sense. And it's actually not obvious, in fact, it's not always true that we actually have such a well-defined notion of a critical parameter. So I'll come back to this later, but this is a bit subtle that it's actually a question one should ask at all, but it is actually an interesting question. And finally, as we heard earlier this morning, often when we want to understand large finite transitive graphs, we would like to take some kind of limit. Like, for example, in the bounded degree case, you could take a Benjamin-Schramm limit, and you can ask, to what extent can one read off the behavior of the finite graph from the infinite limit? Okay. Now, unfortunately, neither of these sets of classical tools that have been used to study percolation, either on infinite transitive graphs or on complete graphs and things like that, neither of these work very well in this setting. There are a few reasons why. One is that often, if you take these infinite volume arguments and you just try to run them, they will often tell you something. It just won't be what you want to know. And like, for example, one thing that happens is that if you look at, so in the infinite graph case, we just have infinite clusters. That's the thing we're always interested in. But if you look at how that sort of generalizes to finite graphs, there's more than one natural generalization of an infinite cluster. There's a giant cluster, which is usually what we're really interested in. And then there are clusters that are merely divergently large. And the thing is that the infinite graph arguments tend to tell you stuff about divergently large clusters rather than giant clusters, which is usually not what you want to know about. And even then, they probably just don't like, for example, we saw like, if you take the Burton-Keane proof and you try to run it, you get some information, or like the Eisenman-Kester-Newman one is actually better quantitatively. So what that one tells you is that like if you take, for example, a particular edge, it's unlikely that both of its endpoints are in distinct large clusters, right? That's kind of a uniqueness thing, but it's like a local uniqueness. You know, it's saying that if you do have multiple giants, they can't have like a space-filling boundary, you know, between them, like an space-filling interface, which is interesting, but it's a much weaker statement than saying you can't have multiple giants. Okay. Moreover, if these proofs rely too much on ergodic theoretic techniques, they might just tell you nothing at all. You know, like we saw in this Newman-Schulman proof, you know that you say, you know, the number of infinite components is not random, and then blah blah blah. It has to be one with positive probability if it's finite with positive probability. But you know, this uses essentially this fact that if you have an automorphism invariant event, then it has probability 0, 1, and that's just not true in the finite case, right? It's not even approximately true. It's not that you have probability close to 0, 1, right? It might have probability a half. So you really can't use those kind of techniques at all. On the other hand, you also can't really do the things like you would do in the complete graph and so on, because you're not going to be able to determine exactly where the phase transition is. So you need to do everything in some more implicit way. You're not going to be able to do any counting, exact counting, or exact coupling with some known process or anything like that. Okay. Now, okay, so this is a list of reasons why the proofs don't really work. But, you know, it's also the case that a lot of things you'd like to prove just aren't true, right? So that might sound worse than it is. I mean, we're going to be able to like carve out some assumptions under which we can prove things, but there are counterexamples, so we do need to find assumptions that we can place on that. Okay, so here's a really simple example where you get multiple giants in a vertex transitive graph. Okay, so you take a complete graph and you take its product with an edge, right? So in other words, you take two complete graphs and you add in a perfect matching between them. Okay, so what happens, let's say we take P to be 2 over n, right? So inside each of these complete graphs, we have this Erdős-Renyi graph with n, which is n 2 over n, right? So because 2 is bigger than 1, you have a giant component with high probability, right? On the other hand, if you look at these horizontal edges, there's n of them, each is open with 2 over n. So the number of horizontal edges converges to a Poisson 2 random variable, right? So with positive probability, it's just 0, with good probability, right? So you get these two giants, but maybe they merge, maybe they don't. In fact, both can happen with probability bounded away from 0, 1. So here the number of giant components is really random, and it, you know, can be 1 or 2 with good probability. So on the other hand, if you like thinking about groups and stuff like that, you probably like thinking about, you know, Cayley graphs, and in particular, you like thinking about bounded degree graphs, right? Many people in our community prefer the bounded degree setting, and you might think, okay, well, this example, some weird stuff happens, but what about the bounded degree case? Okay, so here's one example where things go wrong, and this has things you'll complain about as well, but we'll address those next. So let's just consider the cycle of length n, right? And we take P to be 1 minus lambda over n, where we think of lambda as a fixed constant. Okay, so if you look at the set of closed edges, in expectation, there's lambda of them, right? And in fact, as you take n to infinity, this set of closed edges is going to converge to a Poisson process of intensity lambda on the circle. Okay, and you can just see that, you know, each interval between two of these closed edges is a cluster, and so in the limit you're going to get a random, and they will all be giant because these things will be well separated. So in the limit, what will happen is that you'll get a random number of giants, which will basically be the Poisson lambda minus 1 max with 1. And, you know, so in particular, the number of giants can be any positive integer with good probability. Okay. Now, of course, in this example, you still have a right to complain because, okay, it's bounded degree, but P is very close to 1. So, you know, maybe we just don't care about P being very close to 1. It's sort of degenerate. Yeah. In the examples that I know, but I don't think that's, well, no, I mean, in this example, it's 1 or 2, right? Yeah. Sorry, I didn't think enough about answering your question. Okay, so Yeah, in the bounded degree case, the examples I know have this Poisson thing. But okay, so what we can do is we can come up with a more complicated example where we kind of fake the same behavior, but with P bounded away from 1. Okay, and this is a counterexample to lots of things that one might like to be true in this finite graph world. Okay, so what you do is you take a torus, but which is much, much, much longer in one direction than the other. So let's say we take a small n by big N torus with n much larger than n. In fact, we'll take big N to be exponential in small n, let's say 2 to the n. Okay, and it turns out, so what happens in this example, if you zoom in locally near a point, well, of course, to distance small n, you just see the plane, right, the square grid. Okay, and small n is still diverging, so you are converging locally to the square grid, right? So if P is bigger than a half, you have percolation in the square grid, and that means each vertex has a positive probability of being in a divergently large cluster, right? Because locally it sees the square grid, so it can certainly get to the injectivity radius, right? So in fact, what will happen is that each vertex, when you're above a half, has a good probability to wrap around the torus in the easy direction. Okay. On the other hand, you know, if you look at some dual edge, and you say, what's the probability that I belong to a dual cycle of closed edges that cuts the torus? Well, it's exponential in small n when you're above a half, right? But that constant that it's exponential is small when you're close to a half, right? And you've got exponentially many opportunities to have this dual circuit that wraps around and cuts the torus. So in fact, what happens in this example is that if you're just a bit bigger than a half, although you have a positive density of points that wrap around the torus the easy way, there are nevertheless a large number of these dual cuts that stop a giant cluster from forming. In fact, the largest cluster will be like polynomial, like a power less than 1 in the size of the graph. Okay. Now, if you choose the probability appropriately, you can make it so the expected number of these dual circuits that cuts the torus is 1. Okay. It's a little bit ill-defined, right? Because you might have like more than one that you know, overlap with each other or something. But you can imagine, you can make sense of that, and you can kind of find some point where morally the expected number of dual circuits cutting the torus is 1. And in fact, what you can show is that if you take that choice of P and then you take n to infinity, you get exactly the same Poisson limit that we saw on the cycle. So you get these little cuts that slice the torus of closed edges. These converge to a Poisson process, and so you get exactly the same limit where the number of giant clusters is like Poisson -1 maxed with, that should say maxed with 0, maxed with 1, sorry, not maxed with 0. But again, you really get a random number of giant clusters, and this happens, and Pn does not go to 1 in this example. This really happens away from 1. So it's sort of not just because P is going to 1 and things are degenerate. Okay. So another interesting thing that happens in this example is that it's an example where there's this local picture that comes from the Benjamini-Schramm limit, which is just the square grid, does not accurately describe what's going on in the finite model, right? Because basically what happens is when you're a bit bigger than a half, you just don't have a giant cluster on this long torus. But then there's this critical value where suddenly you do have a giant cluster on the torus. And in fact, once you have a giant cluster, you can show that its density is what it should be. It's the density on the infinite lattice. So in fact, what happens is that the density of the giant cluster in the limit actually jumps discontinuously from 0 up to whatever it would be on the infinite grid at that point. Okay. Of course, in the finite case, everything is continuous, but you know, you should imagine you have a function that just grows very rapidly there, and in the limit it becomes discontinuous. Okay. Moreover, if instead of taking big N to be exponential in small n, I took it to be growing faster than exponential in small n, then in fact you would just never get a giant cluster without taking P to go to 1. Okay. Good. Okay. So one of the first sort of major works on the general theory of percolation on finite graphs was due to Alon, Benjamini, and Stacy. So their paper was really about percolation on expanders, but they included a lot of conjectures about what should happen on general transitive graphs. Okay, and it also, some of them appeared separately in a unpublished paper by Benjamini from around the same time. Okay, so basically, as I understand them, although I don't think they say this exactly in their paper, these conjectures are all kind of motivated by this long torus being somehow a worst case example. Okay, so they're kind of saying if you add in some mild geometric conditions that rule out this extremely stretched torus, then you should recover some theory. Okay, and one way you can think about these things, by the way, is that maybe I'll come back to this in a second. So let me start by, there's two conjectures. There's one about existence of giant clusters and one about the uniqueness. Okay, so this first one is about existence. So it says that if the diameter of the graph is smaller than the volume by a log factor, then you should have a non-trivial phase where there exist giant clusters. So, you should have some epsilon that's uniform in n, so that if p is bigger than 1 minus epsilon, then you get a giant cluster with high probability. Okay, and this volume over log volume is exactly what happens in this n by 2 to the n torus. As I was saying, if you took n by something growing faster than exponential in n, you would not get a phase where there are giant clusters, and that's consistent with this conjecture. Okay, so they also have a conjecture about uniqueness, which is that if you slightly strengthen this, instead of saying big O of volume over log volume, you say little o, then you should get uniqueness. So in this case of an n by 2 to the n torus, the diameter is precisely volume over log volume, and there we had non-uniqueness. So they're saying if you improve that a little bit, if you just have little o, so the diameter is really smaller than the volume over log volume, then you should get uniqueness of the giant cluster. Okay, and these are very mild conditions, right? So the point is that for infinite transitive graphs, there's all this powerful structure theory that comes from like Gromov's theorem and related things that says, for example, that if you have an infinite transitive graph that has polynomial volume growth, then it has, well, Gromov's theorem tells you that it's quasi-isometric, or Gromov plus Trofimov, which is for transitive graphs, tells you that it's quasi-isometric to a nilpotent group, right? And nilpotent groups have integer volume growth dimensions. So a consequence of all this theory is that if you have a transitive graph where the balls grow like they're bounded above by some power of their radius, then in fact they grow exactly like an integer power, right? So this is kind of saying you have no fractal transitive graphs, right? They have to have an integer dimension, which could be infinite, but if it's finite, it has to be an integer. And in particular, because of all this, there's a very sharp distinction between the one-dimensional stuff and the 2 and higher dimensional stuff. Like yesterday, I wrote this theorem on the board that you have a phase transition for percolation for an infinite transitive graph precisely when you're not one-dimensional. I don't think I really explained what that means, but there's in fact a lot of equivalent ways you could define that because of all this structure that you have in the being one-dimensional, you can say you have the balls grow linearly, the volume of balls grow linearly in their radius, but you could equivalently define it as them growing subquadratically in their radius, or you could define it as being quasi-isometric to the integers, or you could define it as being two-ended. There's like a bunch of, there's lots of ways of characterizing what it means to be one-dimensional in the infinite case. But in the finite case, things are much fuzzier because, like in this long torus example, well, is it one-dimensional or two-dimensional? Well, it kind of depends what scale that you look at it on, right? It's like two-dimensional for a bit, and then it becomes one-dimensional. But, what's the right, how one-dimensional does it have to be before things kick in, right? It's a very unclear problem. So, these conjectures are kind of saying that the bad stuff happens when you're one-dimensional, and conjecturally the right place where you see that where you're one-dimensional enough is this condition that where you compare the diameter to the volume over the log of the volume. Okay. But other than that you can analyze this long torus fairly easily and compute everything, I'm not sure why exactly you should believe this specific conjecture. Okay, cool. So the first newer result I can report on, so this was joint with Matt Toynton. So we proved kind of a version of this existence conjecture, but unfortunately not with the optimal power of the log. Okay, now I think, you know, for most practical, you know, in quotes, applications you might have of this is fine, because, you know, really in the interesting examples, you really want to understand the case where the diameter is smaller than the volume by like a power, which of course this treats. But you know, it should be volume over log volume, but we don't quite get that from our methods. This constant is not optimal. You know, maybe you could get it down to 20 or something, but getting it all the way down to 1 seems to require a new idea. Okay, so I won't go too much into detail in this, other than to say, you know, I mentioned before in the infinite case, we have all this structure theory that comes ultimately from Gromov's theorem and things like that. And for this finite graph case, we have to use all these much more sophisticated sort of improvements of Gromov's theorem that were developed in kind of the additive combinatorics community like 10 years ago. So mostly, the main thing is this Briard-Green-Tao paper. So they gave very, very strong versions of Gromov's theorem that give you actually useful structure theory even in the finite graph case. And then the extensions of this to transitive graphs, which are not Cayley graphs by Tessera and Toynton, who is also my co-author. So of course, having one of the people who knows all this stuff inside out as a co-author is recommended if you want to work with with this theory. Okay, and I should say we also use a lot this proof of the PC less than 1 conjecture in the infinite case by Domino-Kapam, Goswami, Ralphie, Savara, and Udine. And just to give you a like really impressionistic idea of what's going on here. So basically this argument by Domino-Kapam et al., it really tells you that if your graph is high dimensional enough, then you can prove PC is less than 1. Okay, and for them, high dimensional means that you satisfy an isoparametric inequality of dimension strictly larger than 4, right? So a 4-dimensional isoparametric inequality would say for any set, the boundary is at least its volume to the 3/4. So you need any power bigger than 3/4, and their method lets you prove that you have percolation phase transition in the infinite case. So even just pushing their result to the finite case already requires some work. In fact, we have to increase the dimension to like 12 or something to get it to work. And then you have like this dichotomy where either you're like high dimensional and you can use their methods, or you're low dimensional, and then you understand exactly what the graph can look like because you have all this strong structure theory. You know, and then you have to contend with the possibility that you look high dimensional at small scales and low dimensional at large scales, and you have to like patch these two regimes together, and you know, it gets kind of technical, but that's the basic idea. Okay, I'd be happy to talk more to anyone who's interested. Okay, so what I want to tell you more about, though, in more detail, is this question about the uniqueness of the giant cluster. So here there were already some results. So in this paper of Alon, Benjamini, and Stacy, basically they proved that their conjecture is true for expander sequences. Okay, so being an expander is like the finite graph version of being non-amenable. It means every set which has at most half the vertices has a large boundary. And what they showed is that if you have an expander sequence, then you always have uniqueness of the giant. And moreover, they showed that if your expander sequence converges to some infinite transitive graph, then you can read off everything from the infinite volume limit in the way that you would like. You know, like the giant cluster will emerge precisely at PC of the limit graph, and the density will be correct, and so on. Okay. Now, one thing you might find surprising here is that, you know, for many expanders will converge to a tree or something, right? Like take a random deregular graph or something. And on the tree, you get non-uniqueness of the infinite cluster, right? But their theorem is telling you that you always get uniqueness of the giant cluster in finite volume, right? Now, these two things are actually completely consistent with each other. And the point is that if you have a vertex in your finite graph, locally it will look like the giant is not unique. You'll have some bit of the cluster going off somewhere, some bit going off somewhere else. And in the limit, these will converge to distinct infinite clusters. But in fact, what happens in the finite graph is they do merge just very far away. So you don't see it in the local limit. But in fact, in the finite graphs, there's just one giant cluster. Okay, so this PC versus PU stuff that's going on in the infinite graph case is actually not reflected in the uniqueness of the giant cluster. It is reflected in the behavior of the percolation on the finite graph, but it's something about the metric distortion. Like when you have non-uniqueness of the giant cluster in the limit, it's saying that the paths connecting 2 points in the giant are often very long, so that they're not tight, so that you don't see them in the limit. Okay, good. Yeah. Oh, sorry, a giant cluster is just a cluster that has a linear number of vertices. Yeah. So, because you're doing finite stuff, you have to be a bit careful about the order of quantifiers and so on. But one way of saying, I'm going to actually state some precise things in a minute, but uniqueness of the giant, you can think of as saying the second largest cluster has sublinear size. Okay, good. So, I stated this other conjecture that if you have volume of littler volume over log volume, you should get uniqueness of the giant cluster. Now, this is actually not the approach that we took in our work. So instead, we looked at a different conjecture of Itai. So the idea here is that in this long torus example, where we got the multiple giant clusters, we actually got these multiple giant clusters at the point of phase transition. It was like I have this sort of discontinuous phase transition where multiple giants all emerge. But actually, if I go above that point to a larger value of p, they'll all merge together and I will have a unique giant. Okay. So as such, it might still be true that if critical percolation is really hard to understand. So maybe if we can just cut out the critical point and just look at the supercritical phase, maybe uniqueness of the giant is always true. I mean, it's not true for dense graphs, because we saw this example of the product, the complete graph with an edge. But maybe for bounded degree graphs, you always have uniqueness, provided you're really supercritical. Okay, so I'll come back to actually defining that in a minute. Okay, so this is what Itai conjectured. And this is what we proved, but in fact, we'll prove something much more general than this. That was very surprising to me that we would be able to prove such a general result before we started. Okay, so before I tell you that, let me tell you some precise definitions of what this stuff means. So let's take a sequence of finite transitive graphs. The elements of the sequence, they don't have to have anything to do with each other. It's just an abstract sequence of transitive graphs. Okay, and if I give you a set of vertices in Vn, we'll write the sort of norm of A to mean the density of A, so the size of A divided by the total number of vertices. Okay, and we'll write K1, K2, and so on for the clusters in size order. So K1 is the biggest cluster, K2 is the second biggest, and so on. Okay, so giant clusters are the ones that have size density at least epsilon, for some epsilon, which everything does, but you need to be careful about the quantifier orders. Okay, so now that we have this definition, first of all, let's define what it means for a sequence of parameters to be critical. Okay, so there are two parts of being critical. So the first thing says that if you drop the parameter by a multiplicative factor, then you always get no giants. So if you look at 1 minus epsilon times Pn, then the probability the largest cluster has size at least C goes to 0 for every C. Okay, so this is the part of being critical that says that you're not supercritical. Okay, and then on the other hand, we want to say that if we increase Pn by a small multiplicative factor, we do get at least one giant, right? So if for any epsilon, if you look at 1 plus epsilon times Pn, then you do get a giant with probability 1. Okay, so we saw, for example, in the Oda-Shreni graph that 1 over n is critical according to this definition. Okay, and note that this is just an asymptotic property, like first order asymptotic property. So if we have two critical sequences, then their ratio goes to 1, and conversely, if their ratio goes to 1, then they're both critical together. Okay, and okay, this is a definition, it's fine. The problem with this is that it's not clear that critical sequences actually exist, right? And in fact, they don't always. So what we need to proceed is a definition of being supercritical that does not refer to a critical sequence, okay? So we'll say that a sequence of parameters is supercritical if there exists epsilon greater than 0, ignore this n less than infinity, so that if you drop the parameter by this small multiplicative factor, then the largest cluster has size at least epsilon with probability at least epsilon. So it's saying like you're supercritical if even if you reduce the probability a bit, you still get a cluster, a giant cluster, so a cluster with some density bounded below with probability bounded below. Okay. And in particular, if you do have a critical sequence, then being supercritical is equivalent to the lim sup being larger than 1. Okay, but this makes sense even if you don't have critical sequences. Okay. And we'll say that a sequence of graphs has the supercritical uniqueness property. Well, it means that when you do supercritical percolation, you get a unique giant, right? Which formally what that means, if you look at the second largest cluster, then the probability that it has density at least C goes to 0 for any C and any supercritical sequence of parameters. Okay, so this definition lets us give a precise statement of this conjecture of Benjamini, which is that if you have a sequence of bounded degree vertex transitive graphs, then it has the supercritical uniqueness property. Okay. So this is what we proved, but we actually proved something much more general, that in fact, this conjecture holds not just for bounded degree graphs, but for sparse graphs, meaning that their degrees are sublinear in the number of vertices. Okay, so in particular, like the hypercube, for example, has degrees that are logarithmic, which is a lot smaller than that. You know, we saw that this theorem can't be true, and it's not true in the dense case, right? Because so the dense is the opposite of sparse, right? It means linear degree. So we saw this example of the product of a complete graph with an edge. That's a dense graph sequence, and it doesn't have the supercritical uniqueness property. And you can do lots of variations on the same construction where basically you take some bounded number of dense pieces and then you like connect them together by some linear size number of edges. Okay. And any example like this is a counterexample. But the remarkable thing is that we can say very precisely, these are the only counterexamples that exist. These are the only ways you get non-uniqueness of the giant cluster in the supercritical regime. Okay, so to make that more precise, we'll define what we mean by examples of this form. So we call a graph M molecular, a sequence of graphs M molecular, if it's dense, meaning again that its degrees are linear in its number of vertices. And for each n, we can find an automorphism invariant set of edges Fn, which is going to be like these edges that go between the blobs, so that the size of this set is order the number of vertices, it's linear in the number of vertices. And if you delete the set of edges from the graph, you split the graph into M connected components, which are necessarily transitive and dense. Okay, and we say the sequence is molecular if it's M molecular for some M at least 2. Okay. And the theorem says that the only way that you can fail to have the supercritical uniqueness property is that you have one of these specific kinds of counterexamples as a subsequence. Okay, you have to have a molecular subsequence. Okay, so I should say, the real content of the theorem is saying, if you fail to have supercritical uniqueness, then you have one of these counterexamples. The converse to that is an easy consequence of this general theory of percolation on dense graphs. Okay. Cool. So after we did this, Philip was also able in single author work to to answer this problem of when you actually have a well-defined critical sequence. So it turns out that you almost always have a critical sequence, and in fact the obstructions to this are even harder to come by than the obstruction to uniqueness. So the only way to fail to have a well-defined critical sequence is not just to contain one of these infinite molecular subsequences, but actually to contain infinitely many infinite molecular subsequences for like infinitely many different values of M. Okay, so, in particularly, I mean, this is basically never going to happen in any reasonable example that you'll come up with. Okay, so interestingly, like everything goes kind of backwards to how you would classically do these things for Erdős-Renyi or something like that, where you'd start by computing where the phase transition happens, and then you'd argue you have uniqueness of the giant above that and so on. So we really start by proving uniqueness of the giant using very implicit methods, and then once you have that, you can go backwards and argue that critical sequences are well defined. Okay, cool. And one more result we have, this paper is actually not quite finished yet, but we also get under the same assumption. So if you don't contain one of these bad subsequences, then in supercritical percolation, the density of the giant cluster behaves in the ways that you would want. So it's concentrated, so it's approximately not random in the limit, and it's given by, if you converge to some Benjamini-Schramm limit, then the density of the giant cluster is given by the density of the infinite cluster in the limit, right? Just as you'd expect. Okay, but one thing to stress is that everything here is about supercritical percolation on the finite graph, right? So we saw in the long torus that this result is just not true without this assumption, right? We got this phase where the density of the giant on the long torus was not well approximated by the density of the limit. But once you have giants, and not only that, once you're really at a larger P than where you have giants for the first time, then everything works perfectly. Okay. How long do I have? Okay. Sorry, I hope to spend more time on the proof, but okay, I'll tell you a little bit about the proof. Okay, so a key role in our proofs is played by the theory of sharp thresholds of events. So let me just tell you a little bit about that quickly. So imagine we have an event, A, that's increasing. So if you add more edges to your configuration, you can only help the event occur, right? So this means that the probability of A is increasing as a function of P, okay? And we say that this event has a sharp threshold if the graph of this probability looks something like this. So basically, if it transitions from being close to 0 to close to 1 over an interval that's much smaller than where this transition occurs, like you kind of scale the graph so that this location of the transition is 1. Okay. So there's a lot of theory of when you have sharp sharp thresholds. So in particular, there's a theorem of Talleyrand. Well, it tells you a lot more than this, but one consequence of Talleyrand's theorem is that if you have an event which is sufficiently symmetric, so let's say, for example, that it's invariant under, you have a graph, you have the bits are on the edges, and it's invariant under any automorphism, and the graph is bounded degree, for example, then any event that's sufficiently symmetric like that will always have a sharp threshold, provided that the threshold occurs at a value of P that is subpolynomially small in that, like smaller than, subpolynomially, yeah, so larger than 1 over n to any power. Okay, so for example, the event that you have a cluster of density at least alpha is one of these symmetric events. So in the bounded degree case, for example, this will always have a sharp threshold for free by Talleyrand. Okay. On the other hand, if the threshold the probability where you see the threshold is too small, you don't necessarily have a sharp threshold. So the classic example here is the existence of a triangle in the Erdős-Renyi graph. So there the threshold is around 1 over n, and you don't have a sharp threshold, even though it's completely symmetric. And it turns out the key thing to understand is exactly this question of whether or not the event that the largest cluster has density at least alpha, whether this has a sharp threshold or not. Okay. And basically there are kind of 2 halves to our paper. So in the first half, we show that you have the supercritical uniqueness property precisely when these events all have sharp thresholds. Okay. And then the second part of the paper, we prove that you have sharp thresholds for these events, or rather, the only way to not have a sharp threshold for the event is to look like one of these molecular graphs. okay? And in particular, this sharp threshold thing, this happens for free when the degrees are smaller than any power, just by Talleyrand. So, you know, in bounded degree case or the hypercube case, you don't have to do this second part of the proof. You just need to prove that if you have sharp thresholds for all these events, then you have uniqueness, which again is not an easy thing, but it's, you know, it's only half the paper. So just to give an example here, you know, if you look at the complete graph and you look at the probability that the largest cluster has density at least a third, this does have a sharp threshold, so it looks something like this. On the other hand, if you look at the product of the complete graph with an edge, and you look at what this event looks like, this probability looks like, it will look something like this, or it'll have like two jumps with like a smooth increase in between. And basically this first jump is when one of these giants, you know, you have these two giants that may or may not be merged, right? So the first jump happens when the first giant, when they have to merge in order to get the total density to be more than a third. And then you have a second jump where even just one of them is enough to push the density of the giant up to a third. So you kind of jump up to this probability, which is like the probability they've both merged. That increases continuously, and then it jumps again up to 1 when just one of them is enough. Okay. Good. So maybe I'll just give you this very brief overview of how the proof works. So this is going to be the proof that if you have a sharp threshold for this event that the density is at least alpha for every alpha, then you have uniqueness of the giant cluster in the supercritical phase. Okay, and there's a few steps to this. So the first one that I won't really go into is that if you're supercritical, so in fact, just if you have a positive probability of having a giant cluster, then the probability any two vertices are connected to each other must be bounded below. Okay, this is an argument due to Schramm, and it's, well, okay, in the bounded degree case, it's due to Schramm, and it's a really simple combinatorial thing. Actually, it's basically, it's a consequence of the fact that dense transitive graphs have bounded diameter. And you use FKG, and it's a pretty simple thing. So we know if we have giants, then in fact, any two vertices have a good probability of being connected to each other. And one thing to stress is this is one of the steps, I guess one of several steps, where transitivity is extremely important, because of course this is not true without transitivity. Okay. Then what we do is we use this assumption that these density events for the largest cluster have sharp thresholds to prove that there exists a sequence, a supercritical sequence, that's smaller than our given one, where we know what we want. So in fact, we'll show at this well-chosen smaller sequence, we get concentration of the size of the largest cluster. So the largest cluster is approximately non-random. It lives inside a small interval with high probability. And it's also, we show that there's a unique giant cluster at this well-chosen smaller parameter. Okay, and basically, you know, I'm running out of time to say more about it, but this is like a consequence of the fact that if you have an increasing function, it can't be really rapidly growing everywhere, like its derivative is bounded at most places. You look at like the median size of the largest component, you find some point where it's not increasing too fast, and then you can show, using the sharp threshold theory, that you must have this concentration around any such point where this function is not increasing too rapidly. Okay. Then finally, we need to go from understanding this well-chosen smaller parameter to understanding the arbitrary supercritical sequence that we actually started with. And this is using a very nice argument that we call the sandcastle argument, where we analyze the monotone coupling between the parameter we're really interested in and this well-chosen smaller one. And we basically argue that if assume for contradiction, you have non-uniqueness of the giant at Pn, then you must have some really weird stuff happening in the monotone coupling at Qn, and eventually you can reach contradiction. I think I'll leave it at that level of detail. And let me just end with an open problem. So in the bounded degree case, first of all, when you're working with the finite stuff, you kind of have to argue quite quantitatively. It's just sort of the nature of it. And in particular, in the bounded degree case, we get an explicit upper bound on the second largest cluster, right? So our result was that it's sublinear, but in fact, it shows that the density is at most 1/√log with high probability, okay? This is what our argument gives us. This is a terrible bound, presumably. I mean, maybe there are some examples where it's this big. I really don't know, but the best one, the example we know that makes the second largest cluster the biggest is the 2D torus, where if you look at the second largest cluster in the supercritical case, its size is log n squared. Okay, this is the density is 1/√log, right? So the size is n/√log. So there's a huge gap between what we actually prove is the universal upper bound on the second largest cluster versus what we know can happen in examples. So I think it would be very interesting to try to, bridge this gap a bit. And yeah, I'll leave it there. Thanks again for your attention. Yeah.
So trying to make sure I understand you have this theorem about uniqueness will basically happen if you're not.
Yeah, if you don't have them like a subsequence, yeah.
So in the long torus case,
well, no. So this statement is about uniqueness for supercritical percolation. So what happens in the long torus? It's like you have this kind of critical point. So you have multiple giants, but here you have no giants, and here you have one. So this is kind of the worst thing that could happen. So basically, when you don't have molecular subsequences, which of course is true when you're not dense, right? So if you have a sparse thing, you always have uniqueness when you're supercritical, but you might have this kind of discontinuous phase transition where you have giant clusters at the critical point, then they might not be unique, right? This can really happen, and it's not ruled out by our theorem. Our theorem is just about the supercritical case. Yeah, which is not ruled out by our theorem.
So often you have hypotheses on the diameter as well, and that seems just kind of first thought that seems kind of true. Like,
yeah.
Something else.
Yeah, well, one of the things is that all this structure theory kind of tells you that actually knowing the diameter, even though it is crude, it does actually tell you all that stuff. It's true that if I phrased this conjecture a different way, then maybe we wouldn't need all this structure theory. But in fact, it is the case that once your diameter is not so large, you can actually deduce a lot about the isochrometry and so on.